Okay, as you learned yesterday, LeChatelier's principle says when you stress something at equilibrium, the system tries to undo the stress. And really, that's it in a nutshell. Here are just some basics that you need to be aware of. So if you have a reaction and it's at equilibrium, you know it's at equilibrium because of the double-headed arrow, and you stress it, equilibrium is disturbed for a while, and then equilibrium will come back, the system will come back to equilibrium. It will be a new equilibrium, but the equilibrium constant will be the same.
Will be constant.
Okay, so here are the ways that you can stress. Put the beads down, please. These are the ways you can stress a system. You can change the concentration. You can change the volume. And when you change the volume, we are going to say that you also change the pressure. And you can change the temperature. And now, what I want you to be aware of is for the volume, pressure, and temperature, you're changing the entire system. You can't say that you added temperature to the products. Remember, all of this is happening in a beaker. So volume, temperature, and pressure, it's the entire system that is affected. You can change just the concentration of one reactant or one product.
Changing volume would only affect pressure if it was a gas, wouldn't it?
Yes, and remember in the equilibrium constant, most of the time we are working with gases.
Okay.
Okay. The way that stress can be relieved, or the way the new equilibrium can be established, is by shifting the rate of reaction to the left. So if that were to happen, we would have the rate of the reaction going this way faster than the rate of reaction going that way. Products would be used up and reactants would be made. Or we can shift to the right and more products would be made and more reactants would be used up. Okay. So here's what you saw yesterday. If a reactant or a product is added to a system at equilibrium, the system will shift away from the added product, the added component to decrease the amount that was added. You add C, equilibrium shifts to the left away from C. You add B, shifts to the right away from B. Now, if you removed C, equilibrium would shift to make more C to replace what you moved. If you removed A, equilibrium would shift to the left to make more A. Yes?
I'm a bit confused on something. Sorry to ask so many questions, but I thought, like, how does the concentration of the equilibrium affected if you need two, if two reactants are needed to make a product, and you add reactants, it's not going to make more of the product unless it's the one you're adding to is the limiting factor. Yes, thank you. So is that true?
That's a good question. Remember that nothing is running out. Did you get what I'm saying? Because you're not going to completion. You are never running out of A and B. And so nothing ever limits in this case. Because while A and B is being used up, C and D is producing A and B.
Yeah, but if you're only adding B, that's not going to affect A. And if you're not affecting A, then C and D aren't going to be affected either.
Well, it does.
Okay.
Okay. And where's you here? Pressure. Okay. Here is a trick question in the making for you. The addition of an inert gas does not affect the equilibrium of a system. The addition of an inert gas does not affect the equilibrium of a system. Why?
It wouldn't react.
Yeah. Inert means a noble gas. Noble gases don't React, actually, that's the one that goes in there.
Um,
But if you will take it around the other way, that would be great.
Would make it
Xenon reacts with things though, right?
Very, very, the only, xenon reacts with something that is incredibly electronegative that really will induce it to give up electrons, and it's generally fluorine. Okay.
Is there
Yes.
any gases that you could add that would also be inert that aren't noble?
Probably, but I can't think of them right now. Okay. If the okay, so here we go. If the volume is decreased, equilibrium will shift toward the side with the least number of moles. Least number of moles. If the volume is increased, the system will shift toward the side with the greatest number of moles. Volume is increased, go to the side with more moles. If the volume is increased, go to the side with more moles. Now, write yourself a giant note right here. Only temp changes the value of KEQ. You mess around with concentration, you mess around with volume, you mess around with pressure, things are going to come back to the very same KEQ as you had before. You mess around with temperature, the value of KEQ will change because the rate constant changes with temperature. Okay?
That's because temperature is a factor in that one equation that I forget the name of, right?
The rate constant, yep.
Yes.
Okay. What I would like you to do is treat energy as a reactant or a product. So we go and look at this. Let's say I had an exothermic reaction. I want you to think of it as nothing more than a product in this reaction. If you added heat, like you put a fire under the beaker, equilibrium would shift to the left away from the heat, towards the side that absorbed heat. Got it? If you put ice cubes underneath this beaker, equilibrium would shift towards the heat. All right.
So if it was at equilibrium with heat as a reactant or a product, would it stay room temperature since it would be adding heat and then taking away heat in both directions?
Now there would be a change in temperature, and then there would be a new KEQ, and then there would be a new equilibrium. So this would definitely change, and it's a lot more complicated because there are a lot of thermodynamics in here than anything else. So for the scope of this class, all we're going to say is this, and I gave you the reason that you need is because the rate constant changes. Okay? All right. Let's look at these practice problems. Arsenic can be extracted from its ores by first reacting the ore with oxygen, which is called roasting, to form solid As4O6, which is then reduced using carbon. Here is the equilibrium reaction. Predict the direction of shift of equilibrium position in response to each of the following changes. You add carbon monoxide. Everybody should tell me that it would shift to the left. Okay. The addition or removal of carbon or tetraarsenic hexaoxide.
Right or left?
Okay. Well, first of all, let's look at KEQ expression. KEQ is equal to As4 CO6. Equilibrium does not rely on these at all, so you can add and subtract all you want. It's not going to affect equilibrium at all. It's not even in the equilibrium expression. And I do believe you could all tell me if I removed As4, what would happen? Shift to the right. Okay. Oh, here's one more thing that didn't make the notes. I really should have. The addition of a catalyst does not You know why?
Because it affects the forward and reactive.
Yep. Because it affects the forward and the reverse.
What does it affect?
It does not affect equilibrium, so there's no shift. Somebody says, oh, I added the catalyst, which way did equilibrium shift?
just
You can
speeds it up,
say,
right?
nope. Okay. Predict the shift in equilibrium, in the equilibrium position that will occur for each of the following processes when volume is reduced. Volume is reduced. Remember, when volume is reduced, pressure is increased. All right. The preparation of liquid phosphorus trichloride by the reaction. So volume is reduced. It will shift to the side with the fewest moles of gas, which would be the, how many moles of gas are on the right side? 0. Can't fool you. We tried to, but I couldn't. Remember, this is a liquid. Okay, so definitely it would be a shift to the right. The preparation of gaseous phosphorus pentachloride according to this equation. Shift to the right. Here's 1 mole, 2 moles. This one is just 1, so it's going to the side with the fewest number of moles. The reaction of phosphorus trichloride with ammonia. It's push, not affected. It's not going to go either way. Either way. Let us look at this equation right here. If I increased the pressure, which way would the reactant, would the equilibrium shift? If I
Wait.
increased the pressure,
C, can you explain why that's
just a
not-
minute and I will. Increase the pressure.
Right.
It's still shift to the right, because if you increase the pressure, what happens to the volume? Decrease the volume, can't fool you. Okay, this one? There are 4 moles of gas on this side, and there are 4 moles of gas on this side. So it doesn't need to shift. It cannot shift to reduce the volume of gas particles because they're the same on both sides.
Yeah, but it's just this, just the reaction. What would happen if there were 5 moles on that? What would it?
If there were 5 moles on this side and 4 on this side, it would go to the right. Okay. Nope, we're talking about volume. Volume. I'll explain to you in depth in a moment. Okay, for each of the following reactions, predict how the value of K changes as the temperature is increased. Temperature is increased. Okay. So we have this reaction, and they tell us that delta H is 181 kilojoules. Will heat be a reactant or a product in this case? Thank you. It is a reactant. This is an endothermic reaction. Heat is a reactant. So temperature increases, and so when the temperature of this system increases, it will shift right or left. It will definitely shift right, away from heat. Okay. Here we have delta H is negative 198 kilojoules. That is an exothermic reaction. So when you increase temperature, it will shift to the left. Now, that's not what they asked. They said, how does K change as a result of the shift? Well, let's look at this. The KEQ for the first reaction is, pretend that's a K, is NO quantity squared over N2O2. And we decided that equilibrium shifted to the right, which means this quantity gets larger while this quantity gets bigger. What happens to K? K will increase. Yep, okay. Now, for this one, KEQ is SO3 squared. And so what happens here, it shifts to the left, and when it shifts to the left, this gets larger while this gets smaller, so KEQ will decrease. All right. Now, wrapping this up all together, there is a connection between thermodynamics, delta G. Who can remember what delta G is?
Gives free energy at non-standard conditions.
Well, actually, the little zip up here, I should have written that, at standard condition, gives free energy. Tell me what gives free energy tells you about a system. Spontaneity. Spontaneity. So here we go. I'll deal with these two first and then go to this one. When delta G aught is less than 0, is it spontaneous or non-spontaneous? Spontaneous. This would be a very useful thing to remember. When delta G is greater than 0, it is
Not spontaneous.
non-spontaneous. Last period we had a little trouble with that. Non-spontaneous. Can you guess what delta G equals 0 is? At equilibrium. It's spontaneous in both ways. Yeah, it's at equilibrium. All right, now let's go back to K. We talked about K and its magnitude telling us whether the reactants were favored or the products were favored. When K is greater than 1, what was favored? Products favored. When K is less than 1, the reactants are favored. When K is at 1, it is equilibrium. Okay. Would like to draw your attention to this fabulous equation. Delta G is equal to negative rattling. Negative rattling. You can see that knowing the Gibbs free energy, you're able to calculate K, and you could tell people at equilibrium whether there would be more reactants or products formed. And here, if you knew K, you could figure out whether or not things are spontaneous. This would be very handy to know. Here's 2 things for you to watch out for. First of all, the R in rattling is the gas law constant. It's the gas law constant that deals with energy. So it's 8.315 joules mole K. And because you're using a value of K, the temperature must be in Kelvin. Must be in Kelvin. I'm going to leave this alone until we wrap up thermodynamics at the end of the year when everything comes together.
How do you
You'll
tell the
love it.
difference between that R